Okay, so I will be giving a presentation on some of the proofs that I came across for Euclid's Infinitude of Primes theorem. Specifically, I will be presenting on Euclid's own proof that he published all the way in the year 300 BC. And I will also be presenting on Saidak's proof, which is a more modern proof that was published in 2005. Some required context that will help speed along the understanding of these proofs is you will need to know that any two consecutive integers are always co-prime, which means that any two consecutive integers will have a greatest common factor of 1. You will also need to know the fundamental theorem of arithmetic, which states that for any positive integer, it can be represented as a product of prime numbers, and people call this prime factorization. So for example, 43,560 can be written as 2 cubed times 3 squared times 5 times 11 squared. So to start off with Euclid's proof, Euclid's proof sets out to try and prove that for any given list of prime numbers, it is always incomplete. So to start, let there be a list of prime numbers. We'll call them P1, P2, P3, P4, all the way up through to Pi. And let's let capital P be equal to the product of these prime numbers, and we'll let Q be equal to P times 1. So capital P would be P1 times P2 times P3 all the way up to Pi, and Q would be that product plus 1. So because all numbers are either prime or composite except for 1, we know that Q will be either a prime number or a composite number. So if Q is a prime number, then fantastic, you found another prime number that wasn't in your original list, and you've thus proved that your list was incomplete and that there are more prime numbers than you know about. If Q is a composite number, then that means that it can be expressed as a product of its prime factors. But because P and Q are consecutive numbers, then that means that P and Q don't share any factors. And what this means is that Q will be a product of a prime number that was not present in your original list of prime numbers, which means that, you've found a new prime number. So the beauty of Euclid's theorem is that you can extend it to any given list of prime numbers. Let's say you write down every single prime number you know, and you apply Euclid's proof, and you get a P and you get a Q, and either one of two things is going to happen. Either Q will be prime, and congratulations, you found a prime number that wasn't in your list, or Q is not prime, in which case you still get to find a prime number that wasn't in your list because of how consecutive numbers are co-prime and how every number can be expressed as a product of prime factors. So let's go with an example. Let's say our list of prime numbers is 2, 3, 5, 7, 11, 13, 17, 19, 29, 31, 41. So let's get our P by multiplying all these together to get 357,520,873,710. And we'll add 1 to that to get Q, giving us 357,520,873,711. Now, using this as an example, we have our initial list of prime numbers, but we also have Q, and it turns out Q is a prime number, and more importantly, it was a prime number that was not in our original list, which proves that our list was incomplete. And so the beauty of Euclid's proof is that you can extend it to any list of prime numbers, and you'll always find a new prime number. And you can do this for an infinitely long list, and you'll still get a new prime number, and it's great. And if we move on to a more modern proof, which is Saidak's proof, it's also really beautiful and elegant in the fact that it's really simple. And Saidak's proof was published in 2005, and it starts off by, and it's based on the knowledge that two consecutive integers are always co-prime. So for any positive integer greater than 1, Saidak's proof is based on the fact, because that the two consecutive integers are always co-prime, if you multiply those two integers together, you will get a product that will have two unique prime factors. And so Saidak's proof is beautiful because you can keep extending this concept over and over and over again to get more and more and more unique prime factors. So you have n times n plus 1, and that gives you a product with two unique prime factors. But if you kind of do a recursive call of this proof onto itself, you can get the product n times n plus 1 multiplied by n times n plus 1 plus 1. And this will give you another product, this time with three unique prime factors. And Saidak's proof is beautiful because, again, you can do this as many times as you want for infinity. Literally, you can keep going and nothing is stopping you. And because each iteration gives you a unique prime factor, and because you can do this an infinite amount of times, it proves that there is an infinite amount of prime numbers. And using a quick example of Saidak's proof, let's start out with n equals 3. And so our n plus 1 is 3 plus 1, which equals to 4. And if we take the product, like, these two numbers are consecutive and therefore they don't share any factors. But if we take them and multiply them together, we get 3 times 4 is equal to 12, which can be expressed in its prime factorized form as 2 squared times 3, which gives us two unique prime factors and two unique prime numbers. And we can keep going. 12 plus 1 is 13, and 12 times 13 is 156. And 156 can again be expressed in its prime factorized form as 2 squared times 3 times 13, which gives us three unique prime factors and three unique prime numbers. And we can keep going with 156 times 157 being equal to 24,492, which can again be expressed as 2 squared times 3 times 13 times 157, which gives us yet another unique prime number and another unique prime factor. And so Saidak's proof is beautiful because you can extend it infinitely and find an infinite amount of prime numbers. So yeah, that's all for my presentation on the proofs. Thank you for watching.